Hey class, today we're going to talk about balancing chemical equations, and this is found in chapter 4 of your textbook, okay? So quickly, I thought that this slide was maybe a little bit confusing, especially given that we haven't gone over this stuff yet. We'll see that in chapter 5. But it's just a sapling problem, as you can see here. And what it actually says right here is exactly 1 mole, and we don't know what a mole is, but to figure out at least how to solve this problem, we'll look right here. It's nothing more than a quantity, such as saying a dozen means 12. So 1 mole of this particular compound contains how many moles of lead, Cl, and O. And so the way you figure this out is if we write this in, and this is a polyatomic ion right here, what you'll notice is that there's only 1 lead and that there are 2 Cl's because of this subscript, which multiplies every atom within the parentheses, and then there are 4 oxygens. Okay, so think of this maybe as a cornucopia or some sort of fruit basket or something of that sort. And in this entire compound, you have 1 lead, you have 2 Cl's, and you have 4 oxygens. Now, let's consider this. Let's say that this entire thing we'll just call 1. And in this case, we'll call it 1 mole, but let's just call it 1 for now. So for every one of these, how many leads do you get? You get 1. For every one of those yellow blobs right now, how many chlorines do you get? 2. For every blob or yellow blob, how many oxygens do you get? You get 4. And then what we're going to be seeing, especially in the next chapters, what happens if instead of saying how many PBs, CLs, and Os do you see per 1 mole of this, what about per 2.5? And then you multiply every one of these by 2.5 in order to get your answer. But I just kind of wanted to give you a brief snapshot as to what we're going to be seeing. So chemical equations, you can read all of this on your own, but a chemical reaction represents a chemical change. And so what you're going to see is these atoms and elements and molecules, compounds, and how they engage in a chemical reaction, and just reorganizing matter, okay? And again, those symbols just to the right of each compound denotes which phase it's in. So this is hydrogen gas, oxygen gas going to liquid water, and the arrow represents chemical change. And so it's saying that hydrogen and oxygen gases are the initial start materials, and then after the reaction is complete, you should have water. Okay, so we'll say the left side is called reactants and the right side is called products right here. So take a look at this slide. It's very helpful to be able to read these quickly. But what you need to realize is sometimes equations are not balanced. Okay, so if you look at this, notice that you have 2 H's on this side. We have 2 oxygens on this side. But on the product side, we have 2 H's, which is good. But we only have 1 oxygen. Just to make it not look like 20 and 10. And so that's a problem because the law of conservation of matter states that what goes in has to come out in equal quantity. And right here, we're saying that we lost an oxygen along the way. And so we need to be able to balance this equation. And it's pretty clear right here that we don't have an equal number of atoms. On the left side, we have 2. On the right side, we have 2 when referring to the hydrogens. But whenever you are looking at the left side compared to the right, notice that it's not balanced. Okay, left side, you have 2 oxygens. On the right side, you only have 1. So this is what balancing chemical equations is. Okay, so it has to follow the law of conservation of matter, meaning the left side total number of atoms has to equal the right side total number of atoms. And we do this by placing coefficients in front of the entire compound or atom or element that we're speaking of. Okay, and so a balanced chemical equation is one in which you use coefficients in order to cause the left side number of atoms to equal the right side number of atoms. So here's one way we can balance this equation is by adding a coefficient 2 in front of your hydrogen gas and a coefficient 2 in front of your water. Now what this causes is 4 hydrogens right there, because 2 times H2, 2 oxygens. And then right here we have 4 hydrogens, because the 2 times that 2 subscript. And then we have 2 oxygens. Excuse me. And so now you notice that the left-hand side, total number of atoms, equals the right-hand side, total number of atoms. So we do need to figure out what these coefficients do. And they act in a very similar way to how having a subscript in a chemical formula, like if I had NH4, and let's say that was 2, O, okay, NH4, ammonium oxide, you would know that very clearly that 2 would work for that and for that. So really that would represent 2 nitrogens and 8 hydrogens. Or in a similar way, that's what the coefficient does. It multiplies that number by every atom within that molecular compound, and or molecular element, however you want to say it, whatever its identity is. But there are also some laws that govern how you balance chemical equations. So here's what you cannot do. Let's say I gave you H2 plus O2 going to H2O, and you realize that there's 2 H's and two O's on the left-hand side and 2 H's on the right, but only 1 O. You are not allowed to do this just to keep it balanced, okay? Don't ever do that, okay? Because what you just did is you changed the identity of this compound, okay? H2O2 is hydrogen peroxide. And so you are not allowed to add any number as a subscript, okay? It has to be a coefficient that occurs in front of, meaning you can form more than one of these rather than changing the actual compound's identity. Keep in mind that, water is safe. You can drink it. It keeps us alive. You can go swim in it. Hydrogen peroxide will kill you if you drink it. So just keep that in mind, that you don't ever want to change the numbers based on subscripts, but rather you want to add coefficients to the front when balancing chemical equations, okay? So now, if you look at this equation, we added a 2 in front of the H2. And so what that means is now we have 2 groupings of hydrogen gas, okay, which totals 4. And how many hydrogens are on the right? There's 4, okay. Oxygen, we only had 1 as per our balanced equation. You see that? Only 1. And then because we have 2 waters, we're allowed to draw 2 waters, and those 2 waters are 2 oxygens. And so it is balanced. We are good to go. Here's some practice balancing chemical equations. I'm going to show you a trick as to how I solve these. I'm just going to go over a couple of these, acting like we don't see the answers. And really, to be honest, these are trial and error, okay? I'm going to only do, let's say, 2, maybe 3 of these with you, and then I'll leave it to y'all to finish the other ones for practice. And you can Google these. There's plenty of practice examples on the internet. But I will show you my trick to solving these, okay? So this is a very scary, nasty equation, and it's not balanced, okay? I'll prove it to you, because what I'm going to do is I'm going to write left, and I'm going to put right here. And on the left-hand side, we have 1 lead. We have, hopefully you can see that, 2 nitrogens from the nitrate polyatomic ion. We have 6 oxygens right here. 2 times 3, but then we have 4 oxygens there, so that totals 10. 10 oxygens. Okay, next we have 2 sodiums, and then we have 1 sulfur. And that should do us, that should complete what's on the left. Now on the right-hand side, I see 1 sodium, I see 1 nitrogen, I see 3 plus 4, so 7 oxygens. I see 1 lead and 1 sulfur. Okay, sorry, I didn't write that small enough. Now, what we have to do is we have to make sure both sides equal the same, okay? Now, I always try to go through this in the most logical fashion, even though we have the end in sight. We just don't know the process, but we try to make the smartest path to get access to the product or the target. And so we know that the leads both have 1. And so, in my opinion, it's best not to mess with that particular compound, either one, until we have to. For instance, if I mess with the lead on the left-hand side by putting a coefficient, it's going to affect the nitrate that's attached to it and then readjust all the oxygens and nitrogens. If I affect the lead sulfate on the right-hand side with a coefficient, then it's going to change the sulfur and the oxygen. So it's better to just leave it alone for now and only mess with it if we have to. But you may notice that on the left-hand side, there's 2 sodiums. There's 2 sodiums. But on the right-hand side, there's only 1 sodium. So it might be worthwhile to just simply put a coefficient in front of this one right here and see what happens. I mean, we're going to need to increase the amount of sodiums on the right-hand side anyway. So what would that do to our tally on the right-hand side if I were to do that? Okay, well, I see that it would cause sodium to become 2. And it would cause nitrogen to be 2. And it would cause oxygen to be 6, but then you still have that 4 on the lead sulfate. So that would cause oxygen to be 10. And now you have to look back at the equation and see, do things match up? Okay, lead is a match. Nitrogen is a match. Oxygen is a match. Sodium's a match, and sulfur's a match. So even though that would look like a very scary equation, it was actually a pretty simple solution. We just had to add a coefficient of 2 just in front of the sodium nitrate. And hopefully you caught a glimpse as to my strategy. I didn't want to mess with the one that didn't have to be messed with, okay? I opted to not mess with anything involving lead because leads were already balanced. Okay, and so that was actually a pretty easy example. Now let's try the next one down here, the middle right. So in this case, we have calcium hydride plus water going to calcium hydroxide and hydrogen gas. Okay, so on the left-hand side, we have 1 calcium. We have 2 hydrogens from there, the calcium hydride, and 2 hydrogens from the water, so that's 4 total H's. And then we have 1 oxygen. On the right-hand side, we have 1 calcium. From the hydroxide polyatomic ion, we have 2 oxygens and 2 hydrogens, and so that gives us 4 total H's, okay, and 2 O's. And hopefully that's the same tally you came up with. And so how do you balance this? Well, I'm going to try not to mess with the calcium right now because they're the same. In fact, it might be a good strategy to just double the O right here, okay? Now, I know whenever I double that O, it's going to double the, or at least double the H's attached to the H2O, but that's okay. We can figure that out. So first off, we need to increase the number of oxygens on the left-hand side to match that on the right-hand side. So I'm going to place a 2 in front of that H2O and reevaluate what that does for me, okay? So that causes me to have 2 O's, but now I have 2 H's on the calcium hydride and 4 from the 2 water molecules, so that gives you 6 H's. And so now our calciums are balanced, our oxygens are balanced, but our hydrogens are not. And so in order to finish this one off, my question is, do you add a coefficient here or do you add a coefficient here on the right-hand side to increase the number of hydrogens, because those are the 2 locations of hydrogens? I'm going to warn you, do not do this one, because if you put a coefficient there, it's also going to increase the number of oxygens and the calciums. We don't want to mess with those because they're already balanced. So instead, let's just increase the number of the H2. How dandy is that, right? And so we're just going to add a 2 in front of that and see what that does. So only adding a 2 in front of the H2 is going to increase that to 4, and then we already have the other 2 from the calcium hydroxide, making 6. And now you just evaluate. Are you done? 1 calcium, 6 hydrogens, and 2 oxygens, and 2 oxygens. And that is the answer, isn't it? So that's how you balance that. And this strategy of the left and right, I apologize if I'm making it look trivial or easy. Sometimes you really do get in a bind, and it can be tough to solve and tough to know how to go forward. I definitely try not to put the incredibly difficult ones on quizzes and exams because they can just take a while to solve. So let's finish off with this one, and I'll let you try to figure out the other 2 on your own time. So P4 plus O2 goes to P2O5. And so I always start with drawing left and then right, just to keep tally of where I'm at. On the left-hand side, we have 4 phosphoruses and 2 oxygens. On the right-hand side, we have 2 phosphoruses and 5 oxygens. And though this one looks trivial, it's a little bit more tricky than the other one, just as to like how to get started. And so let's get started by doubling the phosphoruses on the right-hand side to match the 4. So I'll put a coefficient of 2 in front of the diphosphorus pentoxide, which changes our numbers on the right-hand side to read 4 phosphoruses. And now you have 10 oxygens. Okay. And so now that our phosphoruses are balanced, our oxygens are not. So simply put, we just have to add a coefficient in front of the O2 on the left-hand side to match 10. And so a 5 ought to do. And then we have a balanced equation. So yeah, that's exactly what the answer is. So go ahead and on your own time, try to solve these 2. They are a little bit more difficult, okay? And so if you get stuck, it's okay. Just start over. Sometimes you just get off on the wrong foot and then you kind of get stuck. So I would encourage you, if you get stuck, just go back to the beginning, start with your left and right, and play around again. All right, I hope that was helpful, and always email your instructor if ever you have any questions. Bye-bye.